Professor, you can start now. You have 15 minutes.
Okay, thank you. I hope the sound and the video is okay.
Okay, everything's okay.
Yeah. So, hi everyone, welcome to my talk. As you can see, first of all, actually, I would like to thank to the organizers for this conference. As you can see on the title, I'm going to talk about the freeness of an algebraic structure, which is called generalized splines. And this is a joint work with Professor Selma Altınok. Before introducing the fundamental concept of this talk, we need another notion which is called the edge-labeled graphs. Let G be a connected finite graph. Here V is the set of vertices, E is the set of edges of G. R be a commutative ring with identity. I denote the set of ideals of R, and alpha is a function that labels each edge of G by the ideals of R. We call alpha an edge labeling of G. The pair G alpha is called an edge labeled graph, and the ring R is called the base ring. Let me give an example like this. Here we have the tree cycle as the graph, and the base ring is integers here. As you can see, the edge label on this edge, V1, V2, is the ideal generated by 7. The edge label on this edge, V2, V3, is the ideal generated by 2. And you can see the other edge label like this. To simplify the demonstrations, we don't use the generator brackets. We just write this one. We just use the generators of the ideals. Now we can give the definition of generalized splines. A generalized spline is a vertex labeling on an edge labeled graph G alpha, such that for each edge UV, the difference on the adjacent vertices is an element of the corresponding edge labeling ideal. Let me give an example like this. Just consider the first edge labeled tree cycle. A generalized spline on this graph can be given by 2, 16, and 26, which means that we can just label V1 by 2, we can label V2 by 16, and we can label V3 by 26. Now you can see the spline conditions like this: FV1 minus FV2, which is 2 minus 16, which is equal to minus 14, and this is an element of the edge labeling ideal generated by 7, and the other spline conditions also holds like this. We can talk about the algebraic structure of generalized splines. The set of all generalized splines on G alpha with base ring R is denoted by RG alpha, and this set has a ring structure with component-wise addition and multiplication. Also, this set has an R module structure with component-wise addition and scalar multiplication. After giving the algebraic structure of generalized splines, we can talk about the motivation of the theory. As you can see in here, we just solve a puzzle on a newspaper, something like this. What it comes from, I can talk about it right now. Assume that we have a GKM manifold X, which is a manifold equipped with a nice torus action, and the name is given by the three mathematicians, Goreski, Kotwitz, and McPherson. The generalized splines arises from the algebraic topology and algebraic geometry. If you have a GKM manifold X, you can find its moment graph Gx alpha, which is an edge labeled graph, and then the equivariant cohomology of X is just the same as the generalized splines on Gx alpha with the base ring, polynomial rings with complex coefficients. Details on this motivation of the theory can be found on the paper of Juliana Chimosko. I can just put it on the references, you can see it. So now we can talk about the main concept of this presentation. We first define the submodule of RG alpha, which is MV. If we fix a vertex V, the submodule MV is defined as the generalized splines such that the component on the vertex V is 0. We call this submodule by MV. By theorem of Juliana Chimoska and the others, we have RG alpha is direct sum of R the base ring and the submodule MV. We can just know this equality. Let me give an example right now. Just consider the edge-labeled graph again. Just fix V1, the vertex V1, then MV1 is given by these two generalized splines, which means that the generalized splines on this edge-labeled graph, whose component on V1 is 0, is generated by these two splines. Okay. We have now another definition, which is the edge-label ideal. Given an edge-label graph G alpha, we define the edge-label ideal IG by all the edge labeling ideals like this. Alpha UV, UV is in the edge set of G alpha. Now we have two short exact sequences. The first one is canonical short exact sequence, which is much more clear, I think. IG, from IG to R, the base ring, and from R to the quotient ring, R over IG. And we obtain from here, from this short exact sequence, projective dimension of IG is just equal to projective dimension of this quotient module minus 1 if projective dimension of this quotient module is greater than 0. We have another short exact sequence like this. Here comes the MV actually. Another short exact sequence can be given as follows. From MV to Rn. Here n is the number of vertices of G alpha, and from Rn to Ig, which is the edge label ideal. And here we have projective dimension of MV, the submodule, is just equal to projective dimension of Ig, the edge label ideal, minus 1 if projective dimension of Ig greater than 0. Now we have the main result of this talk. Assume that R is the polynomial ring with two variables and G is a cycle, then Rg alpha is a free R module. Let me explain the proof. Let me give the sketch of the proof actually. First of all, projective dimension of R over Ig, the quotient module, is less than or equal to 2 by the Hilbert-Syzygy theorem. Then if projective dimension of this quotient module is positive and projective dimension of Ig, the edge label ideal, is positive, we have this equality, which means projective dimension of MV, the submodule, is equal to 0, which means that MV is a projective R module since the projective dimension is equal to 0. Then Rg alpha is also projective since Rg alpha is a direct sum of two projective modules. And finally, Rg alpha is a free R module by Coulomb-Suslin theorem. Because of all free modules are projective, we know it, but not all projective modules are free, except if the base ring is the polynomial ring, which this is the statement of Coulomb-Suslin theorem actually. So we have some examples. The first one is if G is not a cycle, then Rg alpha may not be free, even the base ring is Kxy, the polynomial ring with two coefficients. Here is the example. And also, if R is not the polynomial ring with two variables, then Rg alpha may not be free, even the graph is a cycle. How do we know this one or this one is not free? We can use some computer-aided softwares like Cocoa or Macaulay 2, and this gives us the freeness of these computes, some computations, and gives us the results. Also, one last word I can talk. Our results are not limited with cycles or the polynomial ring with two variables. We can extend our results to some type of graphs and to multivariable polynomial ring under some restrictions, but we have only 15 minutes here, and I think that's all to talk. Here are my references, and thank you all for your attendance.